Hi, I wanted to show you an LU decomposition example from start to finish without any minimal mistakes or any problems with it. What I'd like you to notice is that I took this matrix over here, or this system of equations, and built a matrix of coefficients as well as constants that it was equal to. Notice the familiar form of AX equals B. What you're going to want to do is take that original coefficient matrix and build it into a lower and upper triangular matrix decomposition. And the way that you do that is by looking at your original coefficient matrix and basically making zeros in the three entries, in this case below the main diagonal. What I'm highlighting here is that the first thing I want to do is make a zero in this second row, first column entry. When I look at -3 and -12, I think I could take -4 of this first row plus 1 of this row, -4 of the first row plus 1 of the second row, and I want that to replace the entries in this second row. Notice that I keep the first row the same and the third row the same because I'm only affecting the second row. And that's what this elementary matrix will do. Notice that 1, 0, 0, if I multiplied it out, is basically going to keep 1 times -3 with a bunch of zeros, 1 times -1 with a bunch of zeros, and 1 times -2 with a bunch of zeros. So once again, -3, 1, -2, and likewise with the bottom row stay the same. By doing that, -4 of the first row and 1 of the second row, I get 0 from positive 12 plus 12. I get positive 6 from -4 plus 10, and I get positive 2 from positive 8 minus 6. That gives me a matrix that's slightly different. If I continue this, I just took that matrix and continued and said I want to make another 0. That means I'm going to need 5 of this row plus 1 of this row to make a 0 in the third row. That's what this is saying. 5 of the first row plus 1 of the third row are going to replace the entries of the third row, leaving the top 2 rows the same. So notice how the top 2 rows do not change at all. So if I follow that, 5 plus 1 of these. -15 plus 15 is 0. Positive 5 plus 13 is 18. -10 plus 12 is 2. And I continue the process one last time. What I'm going to do this last time is that basically I want to take and look at these two rows, or these two entries, 6 and 18, and make a 0 in this entry right here. In order to do that, I need -3 of these plus 1 of these. -3 of the second row plus 1 of the third row replaces my answers in the third row. The top 2 rows stay the same. So once again, -3 of this plus 1 of this is going to still give me 0. -3 of this plus 1 of this, -18 plus 18 is 0. -3 of this and 1 of this, -6 plus 2 is -4. And that will be my upper triangular matrix. My lower triangular matrix is just the inverse of all of the operations that I did in my elementary matrices. So notice that I had a -4, a 5, and a -3, while my lower triangular matrix will be the inverse of those operations. And since they were all adding or subtracting, I just do the opposite of those, or the inverse of those, and this will be my lower triangular matrix. What I'm going to show you now is how that's going to be used. In order to solve this, I just took my upper and my lower matrix and just kind of copied it from the page before. What definitely is noteworthy, I think, is this concept that, okay, I start off with AX equals B. I change A into a lower and upper triangular matrix decomposition. I get that lower triangular matrix from a series of elementary operations, which I can then find the inverse of in a reverse order to be able to find what I'm looking for, and basically end up with this lower times upper triangular matrix equal times some x, my answers equals b. I'm going to substitute and then go from there. I'll come back to that in just a minute. So the first step is just kind of organizing that now I have this lower and my upper triangular matrices right next to each other. What I need is my lower triangular matrix times a dummy variable's y equals b, which is those constants from the original equation. Now if I look at this, I can see that I have one of these, none of these, none of these. It's very easy to start building equations with forward substitution to be able to solve it. Forward substitution because I'm starting with the first variable and going forward from there. So 1 excuse me, 1y1 equals 15. 1y1, 0y2, 0y3 is equals positive 15. So obviously y1 is equal to 15. 4y1s plus 1y2 plus 0y3 is equals 82. Well, I can just substitute that 15, which was y1, and solve it from there. It's just simple arithmetic that 4 times 15 is 60. Subtract 60 from both sides, and I get y2 equals 22. Remember, this is a dummy variable I'm going to be using later. And then negative 5 of the first plus 3 of the second plus 1 of the third equals negative 5. So if I just substitute, I can say negative 5 of 15 plus 3 of the 22, those two answers I just got, plus y sub 3 equals negative 5, that value that's here. To finish this off, I have basically negative 75 from this, positive 66 from that, plus y sub 3 equals negative 5. A little bit of arithmetic, adding 9 to both sides, and I get that y sub 3 equals positive 4. What I've basically done is I've solved it in this equation for y. Y, that's a dummy variable that I'm going to use later. So the y is those combination of three values, 15, 22, and 44. So to finish off this equation, I just basically take my upper triangular matrix times x, the x that I really want for my final solution, equals y. Upper triangular matrix times the dummy variables equals the constant from the original equation. And now I'm far enough that you can probably see your way to the final answer. Now backwards or Gaussian elimination, where negative 4z equals 4. So y or z must equal negative 1. There's a third of my answer. 6y plus 2z equals 22. Well, now I can substitute the negative 1 in for my z and solve. That's 6y minus 2 equals 22, or 6y, when I add 2 to both sides, equals 24, so y equals positive 4. That's the second part of my answer. And then lastly, using the final equation, negative 3x plus y minus 2z equals 15, substitute the pieces that I know. For example, negative 3 times something I don't know, plus 4. The 4 comes from its 1y, 4 equals 4, minus 2 times negative 1. The negative 1 comes from the z that I saw before. 4 plus 2 is 6. Subtract 6 from both sides, and I get negative 3x equals 9, or x equals negative 3. So my final answer is x equals negative 3, y equals 4, and z equals negative 1. I hope this at least shows you an example of how to solve something using LU decomposition. I'll make sure I save this as a PDF and throw this example as well onto Moodle so that you can study this as well as your book to help you solve the one problem from your assignment, number 45. This is something that I'll expect you to do on a quiz or on a test to come. Thank you.